All right, today we're diving deep into one of the absolute cornerstones of modern tech and math, the matrix. So, have you ever wondered how a simple grid of numbers can power the incredible 3D graphics in a video game, or help solve mind-bogglingly complex equations? Well, these grids of numbers, these matrices, are the unsung heroes working behind the scenes. And today, we're going to pull back the curtain and see exactly what they are. So, what is a matrix? Well, at its heart, it's just a simple grid of numbers. Seriously, think of a spreadsheet or even a tic-tac-toe board. It's just an organized collection of information in rows and columns. And believe it or not, that simple structure is what makes them so incredibly powerful. And they can look all sorts of ways, right? You might see a tall, skinny one that's just a single column, a long, flat one, a neat little square, or a truly massive grid. But here's the amazing part. No matter what they look like, they all play by the exact same set of rules. And that's what we're here to learn. Okay, so here's the plan for today. We've kind of touched on what a matrix is. Next, we're going to dissect one to understand its anatomy, look at the most common types you'll run into, get into some really special cases, and finally, see how we can transform them. All right, first things first. Before we can do anything cool with a matrix, we've got to understand its basic layout, its anatomy. The first thing you need to know about any matrix is its order. And that's just a fancy word for its size. The key rule? It's always rows first, then columns. Always. So if you see a matrix with 3 rows and 4 columns, we call that a 3x4 matrix. Simple as that. Okay, what about the numbers inside the matrix? We call those entries or elements, and every single one has its own specific address in that grid. So, how do we find it? Luckily, the address system is super simple, and it follows that same rule we just learned. Row first, then column. We have this little notation for it. A with a subscript ij, where I tells you the row number and j tells you the column number. Just burn this into your brain. Rows, then columns. All right, let's do a quick check to see if you've got it. Look at this matrix. What's the entry at position A32? Let's see. 3 means the third row, and 2 means the second column. Boom. The entry is 7. Awesome. So now we can read a matrix and pinpoint any entry. Let's start building our field guide to the different species of matrices you'll find out in the wild. We'll kick things off with the 2 easiest ones. You've got your column matrix, which, you guessed it, has only 1 column. And then you've got your row matrix, which has just 1 row. You'll see these pop up a lot when you're dealing with things like vectors in physics or computer graphics. Okay, now this next one is a big deal. The square matrix. This is any matrix that has the exact same number of rows as it has columns. Think a 2x2, a 3x3, a 10x10. These guys are super important and have all sorts of special properties. In fact, they're so special, they've got their own little family of unique variations. And speaking of those unique variations, let's dive into the specialists. These are all square matrices, but each one has a very specific and very useful structure. First up, the easiest one to spot from a mile away, the zero matrix. It can be any size, really, but the rule is simple. Every single entry is the number 0. In the world of matrix math, it pretty much acts just like the number 0 does in regular math. Next, we've got its celebrity cousin, the identity matrix, which we usually just call I. This is a square matrix that has ones running right down the main diagonal, from the top left to the bottom right, and zeros absolutely everywhere else. This thing is the matrix equivalent of the number 1, which makes it incredibly powerful. Now, a diagonal matrix is kind of like the identity matrix's more chilled out relative. It's also a square matrix, and all the non-diagonal entries are 0. But here's the difference. The numbers on the diagonal can be anything they want, not just ones. So think about it. Every identity matrix is a diagonal matrix, but not every diagonal matrix is an identity matrix. Okay, for our last section, we're shifting gears a bit. We've been identifying different types of matrices. Now we're going to talk about actually doing something to a matrix, one of the most basic transformations out there. It's called the transpose, and the idea is actually pretty simple. You basically just flip the matrix over its main diagonal. The first row becomes the new first column, the second row becomes the new second column, and you just keep going. So a 3x2 matrix flips into a 2x3. It's a simple little swap, but it's a huge deal in fields like data science. So here's a fun little thought experiment. What happens if you take a square matrix, you transpose it, and it looks exactly the same? Well, congratulations, you've just found a symmetric matrix. It's a special type of square matrix that's a perfect mirror image of itself across that diagonal. Just look at this example here. See how the number in the first row, second column, is the same as the one in the second row, first column? And check it out. The same thing happens with the first row, third column, and the third row, first column. It's a perfect reflection. That's what symmetry is all about. Last but not least, let's look at a pair of related types. An upper triangular matrix is where every number below the main diagonal is 0. See how it makes a triangle of numbers in the top part? And you can probably guess what a lower triangular matrix is. Yep, all the zeros are above the main diagonal. This structure is a lifesaver for computers, making it way faster for them to solve huge systems of equations. And that's a wrap on our whirlwind tour of the Matrix Zoo. We've covered a ton. We now know how to read a matrix's size, how to find its entries, and we've met all the key players, row and column matrices, the super important square matrices, and all their special friends like identity, zero, and diagonal. We even learned how to flip them with the transpose and spot the symmetric and triangular ones. So we know who all the players are now, but what happens when they actually start to play together? What happens when we add them, subtract them, and multiply them? Well, that's where the real fun begins, and we're going to cover all of that in part 2.